circulation in the atmosphere. The surface ocean are driven by the atmospheric wind. That also we have seen. So we saw winds cause the coastal upwelling. Ekman transport pushed the water offshore, and then it must be replaced by water coming from beneath, and that is called the upwelling of deep water. I'm going to share my desktop. Okay. Uh, you all can see the circulation pattern, wind pattern on the screen, right? Let's talk about the easterly winds. So, when we talk about the southeast, when we look at the southeast trade winds, as they move towards the equator, so where would the water move, the coastal water move? In which direction would the coastal water move? Let's say I'm taking these winds, right? So what would be the effect of these winds on the surface water? On the surface water
They
near
will
the uh-huh. Someone
there would
was
be a felling. A
y-
felling might have.
yes, upwelling will happen. But my question to you is where would the surface water move? In which direction? Let's say this is positive direction and this is negative direction. So would it move in positive direction or would it move in the negative direction? I'm talking about this is
Uh,
southern hemisphere. Do
Negative.
remember? Yes, negative direction. So what we observe is in this direction, right? And
Yes.
same, yes. And same for the northern hemisphere, the water would move in this direction, right to the direction of the wind. And in the southern hemisphere, left to the direction of the wind. So, what is the effect of the surface water moving away from the continent? We get the upwelling. Now, this is secondary effect as well. We are talking about the Pacific Ocean. Uh, so the trade winds are moving the water away from the continent, and this water actually piles up in the western side of the ocean. Okay, here we get the piling up of the water. That's the effect of the trade winds in the Pacific Ocean. The water is upwelled in the eastern equatorial side. Let's use the blue color for this. So this is the eastern equatorial side of the Pacific Ocean. We get the upwelling in this area, and the water is pushed away. The surface water is pushed away, and that water actually piles up here. So let's see what's the effect of this piling up of the water. Okay, let's first talk about the atmospheric circulation in Pacific Ocean. Okay, this is the Andes side, the eastern equatorial Pacific side, and this is actually the Asian side, the Indonesian side, Western Pacific side. So as the warm water is piled up in the western side, what happens? This is not just the warm water piling up; these are the warm wind as well. So the western side actually develops low pressure. How does it develop low pressure? Someone? Uh, I mean, I'm already telling you that there's a low pressure, but how this low pressure is created? How do we get a low pressure zone in the western side of Pacific? Aditya, you have raised your hand.
Yeah, ma'am, I have a doubt because I
Okay.
couldn't understand why are the easterly winds blowing? Because uh, you said that the water is getting pushed towards the west, right? But the wind is blowing
Oh,
from
okay.
southeast.
Okay. Easterly winds, why are they called easterly? Because their origin direction is east. Okay. Uh, this is east and this is west, right? So the direction of their origin is actually east and they are moving towards west. But the naming of the winds is done in such a way that the origin of the area is considered. So if they merge here, if the winds are merging here, their origin was towards east and not towards west.
Yes, I that I could understand, but the easterlies are blowing from east towards west,
Yes.
but the trade wind cannot bend to the west, right? Because the Coriolis force is least at the equator.
The trade winds cannot.
The trade winds cannot blow towards east or west at the equator. I mean, parallel to the equator, right? Because the Coriolis force is least across the equator.
Aditya, you are saying that they cannot bend.
No, no, I meant the
Uh,
wind can bend. I mean, from northeast to southwest,
hmm,
from southeast to northwest, but it
hmm.
cannot blow across the. I mean, along the equator, as it's seen here, right? Parallel to the doldrums, the pink lines, pink arrows.
Okay, so you are saying that parallel to the equator, it's not possible for
Yeah,
the winds to move.
yeah. I mean, solely based on Coriolis force. I might have missed some factor, but I don't know about them.
Uh, okay, Aditya, let's consider. Where should it for it? Okay, let's consider this is our Earth and this is the equator, and this is something like 30-degree north, and these are the longitudes. So uh, the winds that originate from here at 30-degree north, since it's a high pressure zone, we are talking about the superficial winds, okay? And this is a low pressure zone. So the superficial winds should be moving from high pressure zone to low pressure zone. So this should have been their path. But as they move in the vertical direction, the Coriolis force acts on them and it deflects them. Uh, the deflection gives it this direction. Okay, but let's
Yes.
say if there are winds blowing parallel to the equator, right? The Coriolis force comes into action when you're crossing the latitudes, right? But if you're along a latitude, there is no effect of Coriolis force,
Yeah.
right? So winds can be parallel to the equator.
Yeah, but what is the source of that easterly wind? I mean, across the
No,
equator,
no,
the
no.
pressure
These are
difference
the
is not
easterly
significant.
winds. These are the easterly winds, and the pressure gradient is the
Okay.
source of those winds.
Yeah. Yeah. Then what is the source of this wind arrows parallel to the equator, which you have drawn here? Like, yeah,
Okay,
those
these
ones.
these arrows.
Yeah. Yeah.
Okay, the thing is, uh, these trade winds. When we talk about the trade winds, so this is the global phenomenon, and we are talking about the global low pressure and global high pressure. Okay, but otherwise too, there can be local low pressure and local high pressure.
Yeah. Okay.
Yes, and
Yeah.
they
Yeah.
can give rise to the wind as well.
Yeah.
This is a very
Okay.
general pattern, but that doesn't mean that there are no more winds blowing except for the easterlies and westerlies. Okay, so
Yes.
there,
Understand.
let's say, this is a low pressure zone and this is a comparatively high pressure zone. We are comparing here. We are not talking about in absolute term. So the winds can move parallel to the equator.
Yes.
That is possible, right?
Yeah. Uh,
Okay.
yeah, but it is also possible that it is moving eastward then, right? Because it's a local fluctuation.
It is moving eastwards by, you mean like this way?
Yeah. No, I mean
Like
from
this
west
way?
to east.
Eastwards.
Yeah.
Eastwards at the equator.
Yeah. Because it's a local fluctuation, right?
Uh, General patterns. If you see in general, okay, in general, there is this constant trade winds, these ones.
Yeah.
Okay, so what will be the atmospheric condition here? That at the surface, there is always a push coming from the
Okay.
higher latitudes, right? So this push
Yes.
is always in this direction. So for the winds, for the winds that are moving along the equator, this will be the easier one. But again, as you said, the high pressure. No, sorry. What are we talking about? If this is a high pressure here, then there is a possibility that the winds can move towards east as well. But do remember, these is not a large area circulation. This is not the global circulation pattern. These winds are not part of the global circulation pattern.
Yeah. Okay. Thank you.
Okay, this is overall picture, and these winds do shift, but the direction. I'm talking about this global image. The direction almost remains same. Aditya, I hope I have not further confused you.
No, ma'am. I have now understood. Thank you.
Okay. And just in case, if you guys have question, it's better to stop me right there because I'm not at the team screen, right? So I'm not able to see if someone has raised the hand. Okay. So
Uh,
moving.
Ma'am, I
Mhm.
actually have a question.
Yes.
There is no hurricane-like thing that is seen at the equator. Is the reason solely because of the Coriolis force?
Yes. Actually, what is the most important part of the the hurricane is it's a low pressure. The center is low pressure, and the wind is coming from high pressure zone, right? And as the move rushes to the low pressure, Coriolis force acts on it and give it a swirl pattern, right? So
Yeah.
that swirl pattern actually arises because of Coriolis force, and that gives hurricane, that makes hurricane a hurricane actually. If there's no swirling, then it wouldn't be called as hurricane, right?
No, actually, is there any other major cause other than this Coriolis force? I mean,
Uh,
why there is no
no,
hurricanes near the equator?
no. Because for developing low pressure, what do you need? High temperature, and we get high temperature at equator. Constant insolation, right?
Yeah.
Right. But despite of that, there are no hurricanes. By hurricanes, we mean there's no swirling pattern in the ocean. That swirling pattern, that vortex arises because of the Coriolis force.
Yeah. Yes.
Okay.
Yeah.
I can't hear
Okay.
anything.
Then we can move forward. Right.
Too much disturbance. I couldn't hear a single word you said.
Okay, so I would request everyone to mute themselves, right? Once you're done asking the question, please mute yourself.
Can
Uh,
you Can you like
Uh,
repeat that part about the no hurricane at the equator once?
Okay, let's draw what happens at hurricane. This is a local low pressure zone. Okay. So what happens when we have a low pressure zone? What happens to the wind movement? On the surface wind, in which direction do the winds move? Come on, guys, you know that.
You
Someone?
mean, you mean to ask like where is the wind? It'll be trying to come towards the low pressure zone, right?
Yes, so it will try to come towards the low pressure zone. So when I say this is low pressure zone, so comparatively the ambient region is at high pressure compared to this region, right? So let's use this color. So what will happen? Sorry. The winds will start. Uh, okay. So that's how we will have the wind flowing into the low pressure zone. Agreed?
Yes, ma'am.
Okay. And now the magnitude of area that we are talking about, that's like thousands of kilometers square of area. Okay, so this is across latitude. It's not taking place at the same latitude. This is across latitude. This is all right. So when the winds try to blow in like this, what happens? The Coriolis force will act on this. Let's say we are talking about northern hemisphere. Okay, and let's talk about this wind, which is coming, let's say, from equator towards pole. So where would it be deflected? In positive direction or in negative direction? In northern hemisphere, in which direction does the wind Coriolis force act to the motion? To the motion of the object, Coriolis force acts to the right or to the left of the motion of the object?
Right.
Someone?
Right.
Right, right. So this positive direction is the right for this. And this wind will actually be deflected like this. What will happen to this wind, which is coming something like this? And don't say this is parallel to the latitudes. Okay, it is changing the latitudes. So this will be further deflected like this. What about this wind, which is coming from pole towards the equator? In which direction would it be deflected, in positive or negative? Someone? Please give the answer.
Negative.
Huh? Negative, right. So this will be the resultant, the one that I'm drawing in the red will be the resultant motion of the wind. So overall we get a swirling pattern like this. And this is called as hurricane. Until unless there is a swirling pattern, that is not a hurricane. We don't have hurricane everywhere where there is low pressure and high pressure. Am I clear? And let's say if I'm talking about equatorial area, this low pressure is exactly at equator. So at this is 0 degree. Let's say this is 1 degree north and this is 1 degree south. At 1 degree north and 1 degree south, there wouldn't be much Coriolis force. Okay, Coriolis force is 0 at the equator and maximum at the pole. So at 1 degree, 2 degree north, 2 degrees south, the effect of Coriolis force would be very less. So we won't get this swirling pattern. Hey, Today is your deadline for assignment, right? I have solved it more
Yes,
or
ma'am.
less for you.
Yes, ma'am.
Hannah? I should not have solved it. But overall, do you all agree with me that at the equators there wouldn't be too much Coriolis force, so there wouldn't be too much deflection of the winds that are coming from high pressure to low pressure zone. So there wouldn't be this deflection of the winds. We wouldn't get this swirling pattern, which is the characteristic of a hurricane. Not just characteristic. That swirling pattern actually makes hurricane. Are we clear on that?
Yes, ma'am.
Okay, good. So we can move ahead. We were talking about the Pacific Ocean, and let's look at the atmospheric condition of the Pacific Ocean. That's what I was asking. Someone has a doubt? Okay. So what do we observe? Uh, okay, so what do we observe that uh, in this area we have the piling up of the hot water, warm water, and this warm water is going to create a low pressure zone. How is it going to create the low pressure zone? The air is going to warm up and expand and rise up, and that will create a low pressure zone here. Okay, and as the air rises up, we discussed in the previous lecture, this is it's going through an adiabatic cooling. So the temperature will drop as it rises up. And as it rises up, the temperature drops, it hits the saturation point, and we get the clouds here. Okay, and uh, okay, these winds,
Ma'am,
huh?
how, I mean, there you told that adiabatic cooling occurs. I didn't understand how it is adiabatic cooling. Can you explain?
Okay, sure. So this is actually known as adiabatic lapse rate. So that is rate of change in temperature with height. Okay, as the air rises up in the height in vertical direction, it loses temperature. But why is it losing temperature? Let's see. So as it rises up, air is going to expand a little. So when that parcel of air expands, what is it doing? It's doing work on its environment by pressing out. So it decreases the amount of energy stored in that parcel of the air because it has done work on the environment. So its temperature is going to cool. I mean, its temperature is going to drop and it's going to become cooler. And that is known as adiabatic expansion. Okay, as we move up in the height, that is comparatively low pressure, right? Someone please answer me.
Yes, ma'am.
Because there is a low pressure with the height. I'm not talking about the low pressure at the surface. I'm talking about in the atmosphere as we move up, there is low pressure. So air is going to expand, and that expansion comes at a cost. It comes at the cost of the temperature. So as the air rises up, it loses its temperature, it gets cooler. Are we clear on that? And that is known as adiabatic lapse rate, adiabatic cooling, because it's not coming at the cost of it has not taken the heat from its environment. It has lost its own heat. There was no Q involved in this. Remember that thermodynamic equation, second law? Someone please tell me the second law of thermodynamics. In the equation form, how do you spell out?
There is no ideal heat engine.
Give me the equation and Is this second law or third law? Okay, give me the first law. Okay, perfect, right. Give me the first law of the thermodynamics. I forgot about the zeroth law. Please.
Total energy.
Right, total
In simple,
energy.
in simple terms, total energy of the universe is constant. Means if you combine system plus surrounding, you will get constant. Means energy will remain constant.
Okay. So, can you tell me in terms of internal energy and work done and heat added? What you have said is right, but from your statement, can you boil it down to
Okay,
change?
if Q is the total
Yes.
energy supplies to the system,
Yes.
then it will be equal to work done by the system
Yes.
along with increase in the internal energy of the system.
Work done by the system and change in internal
In
energy and heat added. Let's say there is no heat added. So whatever work you are doing on the system or by the system, that's going to result in the change in its internal energy. Agreed?
Yeah, it will decrease
It will,
in
right.
its
So change in
internal
internal
energy.
energy gives rise to change in temperature. So as the air rises up, its temperature decreases. Clear?
Yes.
Who asked me about the adiabatic expansion? Are we clear? So can we move ahead?
Yes, ma'am.
Yes. Okay, quick. Uh, okay, so where were we? I was telling you that this is known as Walker cell, and this is different from the cells that we have considered before. Okay. What are the three cells that we had considered before? These were the cells, right? Hadley cell. This is Ferrel cell and this is polar. Okay. When you see the Hadley cell, the motion of the winds are along the longitude, right? Is there a question for me? Someone was someone asking me a question? It wasn't clear.
No, ma'am.
No, right?
No,
Okay.
ma'am. No one
Okay.
asking good. Yes.
Okay. So along the longitude, that is known as meridional direction, meridional. So these are meridional when we are moving along the longitude. But when we are moving along the latitude, that is known as zonal component or zonal direction. So the Walker cell is actually a zonal cell. Okay, whatever we are talking about, it's almost in along the latitude. All the circulation, all the wind circulation in the atmosphere, that is taking along the latitude. So I hope you understand the difference between Walker cell and the Hadley cell. Okay, fine. So let's complete this cell. So the air moves. Not in the atmosphere, the air moves from west to east and finally converges, sinks back at the eastern Pacific. So whenever the parcel of air sinks back, it's going to create a high pressure zone in that area. So in normal condition, what do we have? In the Western Pacific, we have low pressure zone, and in the Eastern Pacific, we have the high pressure zone. Let's look what's happening at the ocean level. So we saw here that the water is going to move away from the continental boundary, and that is going to cause the upwelling. So as the water moves away, what happens? It is replaced by the deeper water, and the deeper water is actually cooler compared to the surface water. So the Eastern Pacific, we are talking about, this is actually the inside the ocean, what's happening. So we will have cooler surface water at Eastern Pacific, whereas in the Western Pacific, what will happen? The warm water has piled up. Okay, and this is called thermocline. We will talk about thermocline, so keep in mind, this is thermocline. At surface, okay, we will take it later. These are the normal general condition in the Pacific. Eastern Pacific, this is actually a high pressure zone. Western Pacific is actually a low pressure zone. And we get warmer water at Western Pacific than the Eastern Pacific. Now, what happens at El Nino? So, do understand that El Nino is a naturally occurring oscillation in the Pacific Ocean. So this is not driven by anything external. It's not the sun or tilt of the earth or not even human activities that is causing El Nino. Because of anthropogenic activities, there might be change, not just might be, there is change in the intensity of El Nino and La Nina events, but as such, these oscillations are not human-induced phenomena. So what happens during El Nino year? There is a breakdown of this water and air cycle. The air cycle that we see here, that the winds are moving from Eastern Pacific to Western Pacific. So they become very weak. Okay, so what will happen if the winds become weak? If these winds become weak, there wouldn't be any upwelling in the Eastern Pacific. Are we clear on that? Because upwelling are the result of the winds. If the intensity of winds is very low, the intensity of upwelling in return will be very low. Are we clear on that? Can I move ahead? Is there any question? Is there any question on what we have discussed till now?
Yes, ma'am. I have one question.
Okay.
Yeah, so I didn't understand why the Walker cell is getting completed when the dry air is rising above. I mean,
No,
why it is
dry air
moving
is not
again towards.
rising up.
No, I mean dry air is moving towards east, right? The upper part of the cell.
Okay, this one you're talking about. Okay. The dry air is moving east, so how is it completed?
Yeah.
Okay. The thing is, the air cannot keep on moving up in the atmosphere. Why is it so? Because this is troposphere, and up in the atmosphere we have stratosphere. Okay, and this
Yes.
is called as tropopause, the boundary in between troposphere and stratosphere.
Mhm.
So stratosphere is much warmer compared to troposphere. So this tropopause actually acts as a barrier for the air. So the air that's rising, it cannot continue rising. So what happens? It is actually deflected.
Okay.
And okay, but don't think that it is deflected only in this direction. Part of the air is also deflected in this direction.
Okay.
Okay, the overall thing is it's deflected, and part of it will be deflected in this direction, and it finally sinks back, and that completes the circular cell. This is one circular cell. We have three circular cells, 3 or 4 circular cells. Let's see it here. You see, all these are actually
Yeah.
Walker cells. So part of the air is deflected towards east and the part of the air is deflected towards west.
Yes.
Okay.
Yes, ma'am. Thank you.
So we were discussing about what happens during El Nino event. So during El Nino events, the intensity of winds is very low. So we don't get upwelling. So what was actually upwelling doing? Upwelling was actually bringing cooler water from beneath. Now there is no cooler water coming on the surface. So this region will actually will be warm. Earlier, that's the general characteristic of the ocean, that eastern Pacific is cooler than the western Pacific because of upwelling. Okay, but since we don't have any upwelling, so there's no point of the winds of this entire entire Walker circulation pattern. This entire circulation pattern will be very weak. So what happens? Earlier, Eastern Pacific was actually high pressure zone because the winds were converging here, and the convergence of winds causes the high pressure. Since there is no convergence of winds happening here during El Nino event, it's going to be at low pressure zone. And you know what is the effect of El Nino on Indian monsoon? Is Indian monsoon going to be more intensified or going to be suppressed? Can anyone answer that?
Suppressed.
Yes, I guess.
Okay,
Suppressed.
good, but why is it going to be suppressed?
Because the warm mass of air basically it's the
Hmm?
monsoon near
Warm
the
mass of
Indonesian
air,
Bay of Bengal.
Droughts
drought.
might occur. So, okay, sorry. I'm
Okay. Uh, you all are right. So monsoon winds come on the Indian subcontinent because first we have low pressure there compared to the other regions. That's why the west monsoon winds arrive. That's how monsoon arrives. Now the thing is, there's not significant low pressure taking place here, right? This is Indonesia, and India is somewhere here beyond this. So this is not very low pressure area compared to this region, and hence the monsoon is going to be suppressed during El Nino years. And what happens at La Nina? La Nina is exactly opposite. This Walker cell is more intensified. So what happens? This is even way warmer, and this is way colder. And as a result, this is going to be very low pressure, and this region, Indonesia and India, are going to have more rainfall events. All right, so we are clear on El Nino and La Nina. Let's switch gears and move to a new topic. What are these? Okay, we're going to look at the vertical profile of some of the parameters with depth. What is the average depth of the ocean? Give me some rough estimate. 5,000, 4,000, 9,000, 6,000. Am I audible?
Yes, I'm audible.
Okay. Give me some rough estimate. What's the depth of the ocean? Average depth of the ocean?
5 kilometers.
5. Okay. It's actually lower than 5. It's something like 3,780, 3,800. Okay. So we are going to look at the depth profile of the temperature. At the surface, I have written 28 degrees Celsius, but would it be always 28 degrees Celsius? It's going to change with latitude, it's going to change with season, it's going to change with the day, the time of the day that we are looking at. So let's say this is 28 degrees. So what season would it be? This is a surface ocean temperature I am talking about. Okay. So this is something like 2 meters, 10 meters, something like that. Which season would it be? Which latitude would it be?
Is it summer?
Summer, right? Latitude, which latitude could it be? Could it be like 60-degree north, 70-degree north, or equator?
Tropical, I guess.
Tropics. Why not equator?
Yeah, it may be equator. I have no idea.
Okay, mostly tropics, summer, not equator, because okay, we will discuss it later. Why not equator? It's a different topic again. So this is the general temperature profile of the temperature profile. So it can change with latitude, it can change with season. And the other thing to notice is at the surface we have almost the surface, almost the constant temperature. Then it starts declining. It starts declining very rapidly. Okay, so this this gradient with depth is known as thermocline. Okay, the surface temperature is solely the function of the insolation, the amount of insolation that the surface layer is receiving. But the gradient, as for the gradient here, that comes because of the wind action. The wind action actually causes the mixing of the ocean. So the surface ocean is going to be mixed with the deeper ocean, and hence we get this thermocline. Now this thermocline can change. This thermocline can be like this. Okay, very shallow thermocline. It could be like very deep thermocline. Again, this depends on what region are we in, and again what season we are in. We discussed upwelling. Okay, can someone tell me what would the thermocline of upwelling region look like? So what is the general characteristic of the region that has upwelling? Mhm.
That thermocline,
Cold.
I guess it should be a bit shallower. Something.
Right. And the surface temperature as well. What would be the surface temperature of a region that has upwelling?
Colder.
Yes,
Colder.
colder. So why is it so? Because it's a very well mixed system. The deeper water is constantly coming on the surface. So the surface temperature would never reach so high, and thermocline would be much shallower, even like something like this. Okay. Okay, good. Let's move to next parameter, that is salinity. Why is salinity high at the surface? It's not
High
necessarily
evaporation.
35, because of evaporation. Okay. So let's say, so where can we have salinity low at the surface? Is it possible?
Upwelling. No.
Think in terms of, let's say Bay of Bengal. Let's say where Ganga reaches the ocean.
Deltas.
Yes, deltas. So what's happening there?
Fresh water is going to enter the sea, so
Yes.
the salinity will be low there.
Yes, salinity will be low there. Okay, and where glaciers are melting, salinity will be low there as well. Right? That's a freshwater input. And in general, where do you find very high salinity?
Polar
Mediterranean
caps.
Sea. Mm-hmm.
Polar caps, I think, where glaciers are forming. I mean, not glaciers, ice caps are forming.
Ice caps, sea ice. You actually meant sea ice. Sea ice are
Yeah, yeah,
forming. So beneath the sea ice, the salinity would be
locally increased.
yes, locally increased because of the salting out, because of the excretion
Yeah.
of the salt. Right. Uh, and now let's move density. So density is determined both by temperature and salinity. So can we have density like this? Where's my pencil? Can we have salinity? Can we have salinity like this? Salinity profile? The one that I have drawn in green? Okay, forget about it. Let's see
Yes.
what's it's possible.
Yeah, because Sir was talking about the ions attracting each other, causing the volume to reduce, hence density will increase.
Okay, okay, okay. So you meant the density will increase. So what about, let's talk about the water mass that is here and the water mass that is just beneath this water mass. So what's happening? The density at the upper water mass is actually more than the one that is in this purple box, right? Agreed?
Yes, ma'am.
What will happen? Can less dense water sustain more weight, more dense water here? Buoyancy. What is actually buoyancy? Archimedes principle. What is going to float? What actually floats? Something that is denser or something that is lighter?
Lighter.
Lighter. So do you think this water mass can be sustained here, which is actually more denser than the water mass that is in the purple? Is it going to float?
No.
No, right? So whenever this happens, immediately, what will happen? This water mass will go down and the lighter one will come upstairs. So this profile is never observed. Never, never, never. Density always increases with depth. We cannot have something like this. We cannot have something like this. No, that's never possible. So it's always like this. And pressure also has a role to play in determining the density. Okay, as the pressure increases, the density increases. Okay, are we clear on these profiles? If I ask you to draw profile of the equator or tropics, you will be able to do that. You don't have to come up with the exact numbers, but you can draw their profile side by side, like next to each other, relative to each other. That can be done, right? Right. So, I mean, that will be part of your assignment. That's why I'm asking you. You will be able to draw that. Yes, you will be. Let's move to Sir's slides. Did you guys understand the deep water formation? Or should I go through it quickly? All of you understand the deep ocean circulation? If you all understand deep circulation, then this is going to be part of your assignment. Okay, and then we can finish the class here. Or if you have doubts, if you have questions, you can ask me right now.
Ma'am, when are we going to get our next assignment?
Next assignment, I think after Friday's class. So you will have Wednesday and Friday's lecture combined assignment.
Okay, ma'am. Thank you.
Okay, and deep ocean circulation will be part of it, and you'll be asked questions on it. So if you have questions, ask me right away, because we are not going to take this topic again.
Ma'am, there are some heat these kind of maps. Could you please explain this?
Which one? Heat?
Yeah, some. No, not these ones.
What kind of
Yeah, those are probably
temperature?
the last two slides, I think.
Heat, do you mean the temperature?
Yeah. This
Oxygen
this plot.
potential temperature?
And
Temperature?
also isotope. Yeah.
No, isotope, I don't think Sir touched the isotope.
Okay.
But what is your question? Which graph, which plot, which map should I?
Yeah, this
Temperature?
potential temperature. Yeah.
Huh. So on y-axis we have depth, and on x-axis we are moving from this region is actually the North Pole towards South Pole. Okay. So what do we
Yeah.
observe at about, let's say, 70 degree or 80 degree of north? The temperature is very low. Okay, that
Yeah.
is 0 or even lower, right?
Yes.
Okay. And as we move, let's talk about surface. Then later on, we will come to the deep water. On the surface, the maximum temperature we get somewhere in the tropics and at the equator. Do you see at the tropics the temperature thermocline? Thermocline is more prominent here compared to equator,
Yeah.
right? And as we move to the tropics again in the Southern Ocean, it's more prominent compared to the equator. Either way, the surface ocean has the maximum temperature, something like 20 to 28, something like 20 to 28. And as we move lower in the depth, the temperature decreases. So this is actually the thermocline layer. And at equator, the thermocline is shallower compared to the tropics.
What is the reason of it?
What is the reason of it? At the equator, you have the upwelling. And do remember, this is the Atlantic region. And let's see one more plot. And this temperature was recorded, actually, look at here, July 1970 to January 1973. So in the month of July, this started from northern pole. And in the month of January 1973, they reached the southern pole. So all they have done is considered only the summer months, right? Because in this, when northern hemisphere is having summers, southern hemisphere is having winters. Agreed. So all these temperatures, they are not the average temperature, they are the summer temperature. And now let's look why tropics have more prominent gradient, thermocline. Where was it? I hope it is. Uh, in the summer, if you observe 180 means something like June and July. So in the summers, you observe maximum insolation. This is a plot of insolation at different latitudes. Okay, the one in yes blue is Arctic Circle. Excuse me. So in the month of June and July, actually Arctic Circle is getting more insolation than the equator. But if you look at the equator is almost constant across the year, throughout the year, right? The variation is something like
Yeah.
from 400 to 430. But when it comes to tropics or Arctic Circle, the variation is huge, right?
Yes.
And even more intense than equator. So we were at these lines. We were looking at the temperature.
Yeah, but the thermocline will depend on the intermixing of layers, right? Not only the insolation.
Yes. So at the tropics, the mixing is not so uh, it's not so efficient than at the equator. Why the mixing is efficient at the equator? It has to do with the winds and the Coriolis force.
Okay.
Okay, you are not supposed to say okay. You are supposed to ask why at equator we have upwelling. Did sir show you the graph of the chlorophyll? He did, right?
Yeah. Really.
Chlorophyll upwelling. Is this chlorophyll? I think this is chlorophyll. I'm not sure. Is this chlorophyll plot? This is upwelling plot. This is continental upwelling. And at the equators, we have constant upwelling. So how do we do that? Go to the this and actually we can see from here. Let's try it. These are the winds blowing. This is the easterly wind and in the northern hemisphere, and this is the westerly wind. So what is actually the effect of these winds on the equator? The water actually moves in this direction and this direction. In all, the water is actually moving away from the equator, right? It's always moving polewards,
Yeah.
right? So what does it mean? That at the equator, constantly there is water coming from underneath because the surface water is always moving away from the equator towards pole. And it doesn't mean it's moving right away like this, or it could be just small deflection,
Yes.
but it's constantly moving away. The surface water is constantly moving away, and the water from beneath is always rising up to fill that vacuum. So that is upwelling. So equators have constant upwelling, and that's why we don't have a very prominent thermocline at the equators. See, there is not a very prominent thermocline at the
Yes.
equator. And that's what we saw in the, that's what we discussed in in the thermocline diagram that the upwelling, there wouldn't be a very huge gradient in temperature profile. Okay, and let's move to the deep water. So what is happening? The deep water, the most constant at 2 degrees Celsius, right? And just remember, this is Atlantic Ocean, no other ocean. But that doesn't make difference. It's 2 degrees Celsius everywhere in the globe. Why is it at 2 degrees Celsius? Look, the winds affect only the surface ocean. Winds don't have any effect on the deep ocean. So, and sir has already taught you that this water, this is actually, okay, I can do one thing. Okay, let's forget it. Okay, so this is actually Gulf Stream. Okay, the one in the right, that is the surface currents, the surface ocean currents. They are very warm and they are very saline, very, very high salinity. So as a result, their density is very high. Okay, so as they move up towards the pole, what happens? They become cold, but their salinity is high and they have become cold. So overall, their density is going to be very high. And what we saw, that high density, the parcel of high density water mass cannot be supported on a low dense water mass. So what's going to happen? The water is going to sink in the ocean. Do remember that the sinking is not taking place everywhere. Okay, these are called deep water formation. Deep water formation is taking place only at 2 places. One here and the other one is in the Southern Ocean. Can someone tell me why we cannot have deep water formation anywhere else in the globe? What are the key components? What is the key requirement for the deep water formation? How many of you are here? You know, we are past 3 o'clock. So guys, please give the answer quickly so we can end the class. When does water mass going to sink? When is the water mass going to sink? If it's denser, right? If the surface water is denser, then it's going to sink. And how can it be denser? Two factors control the density of water mass. One is salinity and another is temperature. Lower temperature means denser water. Colder the temperature, denser the water. Okay. So as this water moves towards the pole, what happens? It's already very saline water. Okay. The density is already very high. And on that, the temperature acts, it becomes cold and it's very dense and it sinks. And the other one is here in the Southern Ocean. In the Southern Ocean, what is actually happening? Sea ice formation. So sea ice formation, the water is already cold. There is sea ice formation. And because of sea ice formation, the salt is going to be excluded out of the ice. And the water beneath the ice is going to be very saline. And hence it will sink. So overall deep water formation is taking place at 2 places. One is this branch and the other one is along the Southern Ocean. This blue is the deep ocean circulation. And deep ocean circulation is very slow, something like 0.1 meter, even slower than this per second. So it's very slow, but how do we understand the deep ocean flow? The pattern of the circulation. How do we get to know that? It's through the properties of the deep water mass, like salinity, nutrients, and temperature. I think sir will discuss in the next class about did he discuss this plot?
No, we did.
Okay, so this is at the 4 kilometer depth of the ocean. Okay, so this is North Atlantic and this is North Pacific, and this region is actually the Southern Ocean. What we have done is we have taken the transit of the ocean at the depth of 4 kilometer. So this is the dissolved oxygen content of the water. This is maximum at Northern Pacific and lowest at the Northern Pacific. You know, it keeps decreasing as we move along the branch. So this is a pattern, right? As we move along this branch, the dissolved oxygen content is actually decreasing. So this is dissolved oxygen of deep water. Why is it decreasing? Oxygen is being utilized. How do you utilize the oxygen? Through respiration. So the organisms that are living at the ocean floor, okay, this is actually microbial respiration. So along the path, it started when the water sank, it had 260 micromole per kg oxygen. But by the time it reaches Northern Pacific, it has only 160 micromole of per kg of oxygen left, because there's no way it can exchange oxygen with the atmosphere, because the deep water, once it has sunk, it will upwell only at North Pacific and Indian Ocean. Have I confused you guys, or are we clear on that?
Ma'am,
Ma'am,
deep sea
Mhm.
how concentration of oxygen is how we know the concentration of oxygen at there and
How do we know the concentration of oxygen? We take the water sample,
okay, okay, fine.
and we take the water sample, and don't let it not let it come to in contact with the atmosphere. Otherwise, it will equilibrate. Okay.
I was
Ha,
thinking,
ha,
is
ha.
there any remote way to calculate the oxygen?
No, we no remote way. We need to take the water sample from the depth of 4. And Tanishk, do you have a question? You have raised your hand.
In that map, can you come back to that map?
Which one? Dissolved
This
oxygen or this one?
This
Okay.
one. So you are not sure. So in the Indian Ocean there is no deep current, right?
There is actually upwelling. This is not
Okay.
what kind of upwelling? This is not wind-driven upwelling. See, a general mass balance of world ocean, what does it require? That the sinking water at the polar region, the sinking water that is at Northern Atlantic and at the Southern Ocean, it must be exactly balanced by the upwelling water. So the Indian Ocean, we have one upwelling branch, and in the Northern Pacific, we have another upwelling branch. Okay, the water that is sinking, it has to be upwelled. The mass balance, right? Because
Yeah.
ocean level is not changing. It's almost constant. Okay.
Okay.
This is not
Thank-
wind driven. This is not wind driven upwelling. Do remember that. And this is very slow upwelling. So, okay. And what else? Any more
Yeah,
questions?
so deep.
Uh-huh.
Yeah, I have one question.
Yeah.
So deep water organisms are basically mostly anaerobic, right? So how come they
No,
are
why?
consuming? Yeah, I mean their ecological niche is distributed like that.
Okay. You said anaerobic, right?
Yeah, mostly.
See, if they are on above the ocean floor, okay, they
Yeah.
can use the dissolved oxygen from water. All right.
Okay.
And these are known as apifaunal benthic organisms. If they
Okay.
are inside the sediments on the ocean floor, again, if they have oxygen available, then they will be aerobic. But if we go deep further in the sediments, deep inside the sediments, okay, there might be the case that the oxygen is already utilized by the organisms that were on the surface of the ocean floor, or that were on the upper depth of the sediments on the sea floor. Okay, as you go deep down in the depth of the sediments on the ocean floor, then the anaerobic respiration start. It's anaerobic respiration, it's all the function of the availability of the oxygen. If there is oxygen available, there is going to be aerobic respiration. There's going to be the life form that sustains on aerobic respiration. And
Okay,
that's why
okay.
this plot. The seawater sank in the northern Atlantic. It had 260 micromole per kg of the oxygen, but by the time it reaches northern Pacific, it is only left with 140. Because deep water once sank, it cannot exchange. At the surface, what's happening? The surface ocean is continuously exchanging oxygen with the atmosphere. Okay, gas can dissolve in, but once the water mass is not at the surface, there's no way it can exchange oxygen, or even, as a matter of fact, carbon dioxide or any other gas with the atmosphere. Right. But what can happen? The biology, the organisms living uh, in that water mass, they can change the content of the oxygen. They can utilize it. There is no photosynthesis happening uh, at 4 kilometers of depth, right? We all understand that. We all agree on that. है ना? The photosynthesis is
Yeah.
only at the surface where we have sunlight. That is known as euphotic zone. Okay. Any more questions? Okay, before leaving, why cannot we have deep water formation at other places? Why cannot we have deep water formation at equator?
Uh, because deep water is formed when
Hmm.
cold and dense water sinks down, which is not possible at equator.
When cold and dense water. Now, you don't need to say cold and uh, dense. Okay. When dense water sinks down, but how do they become dense? By salinity, by high salinity, and by lower temperature. Okay, and the equator, we have high salinity, relatively high salinity. We must have got the salinity, potential temperature, oxygen. Okay, we don't have salinity plot. But yes, you are right saying it's not cold. It's not cold enough to make it dense. That's why at equator, and as a matter of fact, even at the tropics, we don't have deep water circulation because the surface water is very low in density because it's very warm. Perfect. Any more questions? And to remember one thing, where did it go? Where did it go? We have deep water formation taking place here, but not in Pacific. Right? There can be cold water in Pacific as well. And let's say they are at the same latitude. They are at the same latitude. So their temperature is, they're equally cold. But why the water is not sinking at the Pacific? What is the other factor that controls the density?
Salinity.
Yes, salinity. So it's not very saline water. Atlantic Ocean, this is the Gulf Stream, and it's very saline, it's very warm and saline. Whereas in the Pacific, that is not the case.
Ma'am,
Hmm.
what is the threshold? Means, is there any threshold like above this salinity and above this I mean, below this temperature, deep water formation can occur? Something like that.
Okay. Deep water formation, when we talk about this, that's like huge water mass and continuous. This is a continuous process. We can have regional, whenever the density changes, so it will readjust. A water column in a regional water column, whenever density will change, it will readjust, but it's on a very small magnitude, on a very small scale. Okay, and these deep water formation, they are continuous and at a, of course, very did sir give you 80 Amazon rivers, right? Something like that. The deep water formation is equivalent to 80 Amazon river flow. Anyways, but as such, there's no threshold. It's all about readjusting the density. Readjusting the density of a water column. By water column, I meant the along the vertical depth. At a large scale, it's only happening in the polar regions. But as such, there's no threshold. See, let's say, for example, if this branch, Gulf Stream, this doesn't, let's say, it's not very saline. In future, assume that it's not very saline. So what will happen? It wouldn't be dense enough to sink, right? So this deep water formation, the flow of that deep water formation will slow down. But as such, no one has given any numbers to it that this is the threshold. Clear?
Yes, ma'am.
This all depends on the region. Every region has different temperature, different density. Okay, so can we end the class here? Any more questions from sir's slide? No more questions, right? All right, then I will see you in the next session. Okay, bye bye.